Okay, so here we are with the next pulley problem. The difference in this problem, as we can see by our picture, is that block A now is resting on a table, and it's going to be moving horizontally, and B is still our larger block, more massive block, and it's still going in the down direction. So in this case, again, we expect when we let these objects go that the 25 kilogram block will be pulling downwards, which will creating this motion where A will be accelerating to the right, B will be accelerating to the downwards direction, according to our picture. So our negative will be on that side, positive on this side for A. So to keep it the same, for B, negative will be towards the top, and positive will be towards the bottom. Okay. So same questions. Choose each block as our system, and draw a force and motion diagram for each. So we're going to start with A being our system. So here's for A. Okay, so our motion diagram. Now we said our motion is going to be going sideways in this, horizontally, and again it's still going to be speeding up. So our motion diagram will have arrows increasing in length. Okay, so time 0, negative direction, positive direction. Our delta V is going in the right direction. Okay. Now we have to make a force diagram for this. So it's sitting on a table. It's a little bit different than the last situation. So force diagram. Top and bottom should be the same length. Top is force table on block A. And the bottom direction is force earth on block A. Make sure we want to label our system as A. Okay, and we have one more interaction going on here, and that is now our string is pulling box A to the right. It's pulling box A to the right. And that is labeled force string on box A. So there's our complete motion diagram and force diagram for our system of block A. So we'll next take the same thing as we did before. System for block B. This one's still going with vertical. This is still going in the vertical direction. So we have our motion diagram and speeding up. And our delta V arrow speeding up, going down. Okay, force diagram again with our patterns. The change in velocity is pointing down, so we should expect that our down arrow, force earth on our object, should be larger than our up arrow. So our down arrow is force earth on object. So earth on block B. Positive direction, negative direction. But now, as we can see in our picture here, we have an object going in a horizontal direction, and then we have a block going in a vertical direction. Okay. It's the same type of interaction that we saw before, where our string, again, we're assuming our string has no mass. We're assuming our string is not being stretched. We're assuming that our pulley has no mass. We're assuming that our pulley has no friction. So we just have the string connected to each of our boxes. So same like our previous example, we should expect that the force string on B should be equal to force string on A, just in the opposite direction. Okay. So that being said, when we make our force diagrams, this arrow here should be the same length as this arrow here. This is going in the positive direction. This arrow is going in the negative direction. Okay, so they are opposite directions. It may be a little confusing that one's vertical and one's horizontal, but that's why it's very important to keep our positive and negative on our motion diagrams, force diagram sketches. Okay, and we will label this force string on object box B. So that takes care of part A. Complete motion diagrams and force diagrams. So C, what is the acceleration of each block? Same thing as before. In the previous example. So start off with a mathematical model. I'm going to make a word statement for this. Acceleration is equal to the sum of the forces divided by the mass. In this case, we're focusing on the direction in which there is going to be some acceleration. In our vertical direction here, we can see that the force that the table on box A and the force Earth on box A should balance each other out. The sum of these forces should equal 0. It's not moving in the vertical direction. However, we do see this horizontal direction. We have one arrow pointing to the right, no arrows pointing to the left. So our sum of our forces, in this case, should be in the positive direction. There's only one force. Again, this sum of the forces comes directly from our force diagram. So this acceleration is equal to the force string on box A. That's the only force we have this time. This is divided by the mass of box A. So acceleration is equal to force string on A. We do not know what the string on A is. Okay, so we're going to keep that as a variable. But we do know the mass. We set up here, the mass is 10 kilograms. So 10 kilograms. Multiply 10 kilograms by both sides. You have 10 kilograms times A is equal to the force string on box A. We'll leave this where it is for now. So we're going to take a look at our system B, box B. Same procedure. Acceleration is equal to the sum of the forces divided by the mass. Here we have two forces, two interactions with box B. So our acceleration is equal to force string on B plus force Earth on box B divided by the mass of box B. Now we can plug in our numbers. Acceleration, we don't know. The force string on box B, we do not know. We can solve for force Earth on box. That is just its mass times our acceleration. Acceleration due to Earth, pulling it down, 9.8 meters per second squared, times its mass, 25 kilograms. This is divided by mass, again, 25 kilograms. Okay, now one thing that I did forget to do up here, again, we want to assign our negative direction because the string is pulling box B in the negative direction, like we see on our force diagram. It's in the negative direction. So we multiply both sides by 25 kilograms. 25 kilograms times A, acceleration. This is equal to the negative force, negative direction, force, string on box. And 25 kilograms times 9.8 meters per second squared is 245 kilograms times meter per second squared. Subtract both sides by 25 kilograms times acceleration. Add both sides by negative force string on box. And we have that the force string on box B is equal to negative 25 kilograms multiplied by acceleration plus 245 kilograms times meters per second squared, or newtons. Okay, so we have two equations, we have two unknowns, same as before. Okay, so we have use a system of equations. Our forces should be equal to each other. So we have set them equal to each other. 10 kilograms times acceleration is equal to negative 25 kilograms times our acceleration plus 245 kilograms times meters per second squared. Subtract both sides, or add both sides, 25 kilograms, and we end up with 35 kilograms times our acceleration is equal to 245 kilograms times meters per second squared. Divide both sides by 35 kilograms. And we have our acceleration is equal to an even 7.0 meters per second squared. So there's our answer to part B. Again, both boxes are going to be accelerating at the exact same rate because they're attached by our string. Okay, so we can move on to part C. And what does C say again? What is the force that the string exerts on each block? Okay, we said that they should be the same. We agree that they should be the same. In our previous example, if you didn't take a look at that, should take a look at that before that, where I actually solved for each separate one. Again, I'm not going to be doing that in this case because we should understand that they're the same force, same magnitude, different direction. Okay, so again, we have our mathematical equation. Acceleration is equal to force string on, actually, let's write the full equation out first. It's always a good thing to do so we don't get confused. Acceleration is equal to sum of the forces over the mass. Okay. Acceleration is equal to force string on box A and divided by the mass of box A. Acceleration is what we found from before. So 7.0 meters per second squared. And that is equal to force string on box A divided by 10 kilograms. Multiply both sides by 10 kilograms. You get 70.0 kilograms times meters per second squared. And that is equal to our force string on box A. Okay. And actually, I'm going to go back and I'm going to do the other one again. I feel that this is actually really important. Something that I didn't show last time that I want to make sure that I show this time. So we'll go back to our previous equation for system B, box B. Okay. So our acceleration is equal to the sum of the forces over the mass we have our acceleration is equal to our interactions again. We can get away from our force diagram. Force string on box B plus force earth on box B divided by the mass of box B. Oh. Yeah, that looks a little bit better now. And now we can plug in our numbers. Acceleration is equal to 7.0 meters per second squared. We're looking for the force string on B. And force earth on box B, 9.8 meters per second squared. Multiply this by the mass, 25 kilograms. And it's all divided by the mass, 25 kilograms. Now, one thing I didn't show before that I want to make apparent here, and that is, again, we choose this force to be the negative direction because that's how it's depicted on our picture, is how it's depicted on our force diagrams. So we want to make sure that we include that this is a negative, and this is important. And we'll see why in just a second. Multiply both sides by 25. Okay. So 7 times 25. And 7 times 25 is 175. That's kilograms times meters per second squared. That's equal to the negative force string on B. 9.8 times 25 is 245 kilograms times meters per second squared. Okay, so we're going to move we're going to move the negative force over to this side, and I actually want to bring out an important point here. And this is the same thing that I did the last time. In this case, when we're solving for this force now, we actually do not want to add in this negative sign. I did it on the first example. I did it on this example too. And the whole point of doing it this time around, the second time, was to show that adding this negative sign on this time is a mistake. And you might be asking why. If I leave this, if I do not have this negative sign here, I will then not be bringing this over. I will subtract both sides by 245 kilograms times meters per second squared from both sides. Okay, this cancels out. 175 minus 245. Again, we end up with 70, and this time it's negative. It's negative 70 kilograms times meters per second squared. And this is equal to our force spring on box. Okay, box B. Now this is what's really important here. And it's something that I confused in the first one. I wanted to make sure I showed it in this one so that we get a clear understanding. They're the same magnitude, 70 newtons, 70 newtons, but it's negative. And the signs actually agree, and they match with our picture, okay? String here, this is force string on 1, pulling this way. And here we have force string on 2, pulling up. Look at our directions here. Going in the positive direction, now going in the negative direction. Okay, so when we're solving out originally, we have to assign our values based on the direction that they're in this first part, because we know that we have to subtract this value from this value because one's in the positive, one's in the negative. However, when we're going back and checking and plugging back into our equations, we no longer have to assign this value. It will come out on its own. That's why we always have the sum of the forces. And that's a very important part. So this concludes the second experiment or second example. There will be one more example after this. It's essentially going to be the same question, except we're making it a little bit more complicated. We're going to be having some friction here. Okay, so a rough surface. And on to the next one.